Coulomb was on the.
Hello,
Hey,
Carl.
Professor.
How you doing?
Good. How are you?
Not too bad. Just looking over some stuff right now. I'm having some difficulties. I've been trying to make a practice test for your class and various other ones, and I've had some technical difficulties. I've basically wasted a couple hours, and it keeps erasing them. So I just
Oh,
finished putting off all my tests in my face-to-face class. I'm thinking about doing the same thing with you guys.
what?
Uh,
Ended up missing Tuesday. When was our scheduled test?
to do tonight.
Oh, well,
Sometime
good.
this week, basically, is what you're allowed.
Gotcha.
How's it going with you?
Pretty good. I'm sitting in traffic right now, but
That stinks. Well, at least we're recording it so you can hear everything and maybe possibly ask questions. Just don't put too much focus on this and not enough on driving. Don't want that to happen.
yeah, I'll just listen in when we're talking.
Gotcha.
So not too bad. But
Okay. It looked like I was just looking at the grades. It looked like a couple people missed my first online test and a couple people missed my second online test. So I gotta figure out what to do about that. All right.
yeah, I think I got all the online tests. I just realized last night I was going to the online tests. So Canvas isn't showing like the Pearson due dates for our homework. So I realized like I'm behind on homework, which I did not recognize because I had been just following Canvas and didn't think like to click on
Oh,
the
gotcha.
Pearson part. So that's my fault. I got to go back and I know they'll be late, but I got to go back and fix all that.
Yeah, definitely do them. And like I said, there might be something where the lateness isn't going to matter ultimately. So you've had me before. You know what's going on.
Yeah. So that's on me. I just blanked out on it. I hadn't been thinking about it. So
Well, I've managed to get so far behind and stuff like that. So I certainly am not going to blame you for that.
I feel like I don't know why, but I just feel like this semester has just been like seems kind of crazy.
Yeah, I'm having difficulties. It seems like everything that normally is pretty easy and straightforward is taking me 10 times as much time, and I'm wasting time. Like I said today, I wasted about an hour and a half, 2 hours making up a test bank that I could use, and I finished and then looked back in it, and it was completely erased.
Yeah, I
So
don't. It's crazy because like the summer semester obviously it was a lot faster, more consolidated, but for whatever reason, I just felt like that
you're
for
more
me
in
at
sync
least it
with
was
that.
just yeah, it just like was like boom, 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 straightforward. This one I've just been struggling. I don't know why.
Yeah, and this class is harder, which is a good thing that it takes longer. But sometimes, yeah, sometimes slightly more relaxed pace can actually be detrimental to some people. You know, I'm one of those. I suspect you are too.
Yeah,
Yeah. Well, we're gonna do some highbrow stuff tonight. We've already worked with the Coulomb's law of force. That's what we did on the last time we met.
last
For some reason,
Tuesday. Yeah,
yeah, that was a week from today. Yeah, a week ago today. So that was Coulomb's law without the vector part of it, but you still had to do vectors and stuff.
yeah.
Now I'm going to give you the electric field and a formula for that, and then work some problems. But they'll be get a little scary, but literally they're probably the second most difficult problems you'll have the whole semester.
Okay, that's good.
Yeah, in other words, you'll see it, and then you'll have a break for a while, and then all of a sudden you're going to see almost identical thing, except now the newest one, the one that's harder, will actually have not only all the ugly integral vector stuff that this one has in it, but it also has a cross product in it that's
Oh man,
integrate. So yay!
yeah,
The
that's
good news
fun.
is with more complexity comes fewer problems that can actually be solved. So
That's already the problem across physics, right? There's only a limited number anyway.
exactly. All right, well, that makes me feel better about this. So I guess I'm just going to have to do that. And uh, I'm curious if my student ended up running out of time. I made a test that I thought was pretty good for the 241 class, and they took it, and well, only one person's taken it so far, and they didn't do that well. And I thought I made it really nice, and this is a good student, so now I've got to I'm thinking about completely revamping it and just putting all y'all's tests to next week.
Okay. For the online, we do it like we did kind of over the summer, right? Where we have that 1 week, we can either go to the testing center or use the mirrored method or
Yeah,
get which
this
one
one
of
I've
you,
been
right?
yeah, this one I've been trying to just get y'all to use the testing center and avoid the whole mirror process. But yeah, that's basically what it is. If I have someone that can't get to a testing center, then I'll figure out some way to either I chaperone it, slash proctor it, or we'll do something with mirrors or something like that.
Yeah. I guess TCC changed their lockdown browser method because my calculus, my differential equations class, they used a different,
Oh yeah.
not respondus. They used something different. You had to pay $15 to do it. But her theory was like, hey, I provide times that I will sit in and proctor it. But if you want to do it at the freedom of your own time, you have to pay the $15. And they like didn't acknowledge that service this semester. So all of our tests, like she couldn't offer the respondus browser.
Oh,
So
okay. So they got something else they're working from the math department at least, huh? Is that a Chesapeake math class, or is that one from Virginia Beach, or do you know?
I think she's from Chesapeake because her syllabus says to like go to Chesapeake for tutoring. So I think it's a Chesapeake.
Gotcha. Who's your calc teacher?
Dale, Pamela Dale.
Yeah, that's a friend of mine. Yeah, I thought that might be her.
I really, really like her
Yeah,
class and her structure.
she is very student centered, and she really likes to work out all the details. She's kind of like me, at least in that respect, except she probably explains it even better. So, yeah, she's a good friend. I've had her for as a friend for 20 years, I think now. We worked at
Yeah.
the old college in North Carolina together.
Oh wow.
Yep. In fact, I think she might have even gone there too. I can't remember. I know me and three other instructors that I knew did. I think she might have, but I at least know she went to Currituck High School, the same place I did, and then later went to Dare County High School. So she's from this area at least.
Yeah. She showed some pictures from the storm last week.
Yeah, because she's out in Greenville or near Greenville, and they got quite a bit worse than we did here on the coast. My my daughter sent me pictures. She was up in Boone. I didn't realize she's literally only like 17 miles away from a good friend of ours that seems to have passed away. Got lost in flooding. Was in her house and with her husband and her dogs, and heard a crack. And they got on the bed, and I mean the bedroom, and then it went on the whole house lifted off the ground basically and started floating down river.
Is
And
that the lady who's there? Her husband's been found.
yeah, Miss Ashby.
Yeah, yeah, I've seen a couple of my friends on Facebook have been posting about they just lost the resources to help finding her. I think Sunday, and so and her daughter was on the news talking
Yeah.
about it.
Yeah, she was a good lady. I didn't know her as well as my former wife did. My girls both had her for I think they both had her for fifth grade, and then my former wife and friend of mine, she played tennis with her, and but she moved away about I think 3 years ago, moved to a different part of North Carolina, so they haven't been as close lately. But still, it's just a really wonderful person. Uh, I don't know how the husband's living. I don't know how the daughters are living. I don't. I just it's just awful. So
It's almost just worse. Not like there's just no answers, right? The
right,
grimness of like the no answers is just so hard.
yeah. I mean, you got to think the worst, but then the worst is still horrible, and the less worse is horrible in another way. So
Right. It's
yeah,
awful.
it stinks. But I got friends living in Florida, and at least this time he's splitting. So he lives just south of Tampa Bay, or I say he, it's him and a couple other people, but his wife and stuff like that. And they stayed for the last one and had a little minor damage, but they're really far inland and they're up high, so they didn't have any flooding. But this one might be so bad, and it's hitting where they'll get the worst side of the hurricane, so that actually might result in more damage. So they're actually going to Georgia
Oh
to
wow,
escape it.
that's great.
Yeah, it helps when you've been in the Navy. You got family all over the place. So, did you hear about Alabama this weekend?
No,
Alabama, number one team in the nation, lost to Vanderbilt, like the traditionally the worst team in the SEC in football.
that's
And
great.
I shouldn't say traditionally worse, but at least lately.
Didn't they just beat Georgia like 2 weekends ago too?
Yep.
In like a
Yeah,
really
yeah,
close
they had
game?
another big win. Yeah. So Vanderbilt's pretty good. They've got some quarterback that basically transferred from, I want to say somewhere out west and decided to go to Vanderbilt. And evidently they interviewed him just before the game. And he said, a lot of people are going to be surprised. He said, but we're not going to be surprised. And then they went out and won. And like never was behind. They were up by like 35 points.
Wow. Is that the one where they tore down the field posts?
Yeah, yeah, and they were selling them online and everything else. So they got
Yeah.
$100,000 for that, but I don't blame the college students. That's what East Carolina did too back a long time ago. We used to play regularly NC State, and they were always better than us. And finally, we beat them one time, and we tore down the goalpost, so they stopped playing us, and they didn't start playing us again until I was in grad school. I want to say this was like 1995, and we ended up playing at the Charlotte Panthers Stadium and crushed them there. And then next thing you know, we started to go tear down the goalposts, but luckily everybody stopped them from that.
Yeah, that'd be a pricier pay.
Yeah, exactly. All right. Well, it looks like we're finally at time, and I've actually got a good cadre of students. Hey, everyone, how are you doing? Please chat your first and last name in the chat box. So I'll have you for roll. And I just decided I'm making an executive decision. I have decided to push the test back. Mainly, you've seen that I still haven't got like a practice test up. I've had a numerous problems, so I just said screw it. Hopefully, I'll get that sorted out and have it all done by tonight or tomorrow, and that'll give you at least through the weekend. Our test is going to be basically. It was supposed to be you were allowed to take it sometime between Monday of this week and Sunday of this week. I'm now going to say from Monday of this week to Sunday of next week. So I'm going to give you all that time to try to knock it out. I looked, no one had taken, yeah, no one had taken it or anything like that. I haven't made the practice tests. That's where the problem's coming in. So I pushed your test back. It's not going to be due this week. It's going to be due next week. And I will put the practice test up probably about the same time as I put the regular test up. And then you can work uh, to make a arrangement with whichever testing center on whichever campus you want. So I hope that's not a problem. If anybody really was looking forward to taking the test this week, that still can be done. You just need to let me know. But generally speaking, it's going to be due next week. I hope that's a positive announcement for you guys. Anybody have any questions before we get started? Okay, I'm not increasing the number of chapters, so the chapters are still going to be on 17, 18, 19, and 20. We are covering chapter 21 right now, but that will not be on the test. So I'm going to try to make especially since it's been such a delay, I'm probably going to try to make a even more exacting uh, practice test. In other words, it's more reflective of exactly what I'm requiring of you, especially in chapters 19 and 20, where I did a little short. So I'll do that. I'll let you know when that's available. Until then, what I'd recommend you doing is, especially chapters 19 and 18, be doing those chapter tests until I get the practice test up, and that should keep you prepared. Or just doing your homeworks for chapters 18, 19, and 20. If you hadn't already done 19 and 20, make sure you knock that out, or even go back over them. Those are good exercises. But to be honest with you, it really is just most of the tests. So, any questions on that or anything else for that matter? All right. Well, what I'm going to do is I'm going to go ahead and jump into covering this chapter 21. When we last spoke, we covered Coulomb's law. And remember, Coulomb's law looked a lot like the law of gravity, the law of gravity being F equals G m1 m2 over r squared, and Coulomb's law for force being K Q1, Q2 over R squared. Okay. I don't really like K, so I'd normally call that Q1, Q2 over 4 pi epsilon naught times R squared, all of that in the denominator. But we have a problem. Specifically, we have a problem that's called action at a distance that everybody knew when we created or when Newton discovered the law of gravity. He knew it was a problem. It was as if, the sun was reaching out across space and pulling on the planets, even though there wasn't a physical attachment between the two. So we had to make some sense of it. And in the case of both gravity and electric force, and even ultimately the magnetic force, what we tried was we imagined that in some sense, so I'll stick it to Coulombs here. So before we had F equals K, Q1, Q2 over R squared, what we're going to do now is we're going to say one of those charges, either Q1 or Q2, I'm going to just call that, say, capital Q. Okay. That charge you can picture as if it messes up or alters space around itself. So if you had just a charge capital Q in space, there's some sort of aura around it, and that aura is what we're going to call an electric field. And it actually is a vector field because the electric field is a vector quantity. So when I say fancy words like field, mathematically, all that means is just imagine creating a coordinate system in any space you're wanting to work in. Create a three-dimensional coordinate system, X, Y, and Z. And then, from the origin, you'll go a certain distance parallel to the x-axis. And when you do that, whatever that distance is, that will be your x coordinate. And then you go from there parallel to the y-axis some distance, and whatever distance that is, that'll be your y coordinate. And then you go parallel to the z-axis from there some distance until you end up at the final point. And that distance will be the z coordinate of that particular point. So you have a ordered triple, parenthesis x comma y comma z. Now, if you take every point in that space and imagine assigning it a x, y, z for each of those points, and then in addition to that, assigning it either a magnitude and direction for a vector or a x component, y component, and z component for a vector. That's what a field is. That's specifically what a vector field is. If instead I took each one of those x, y, and z points and recorded the temperature there, then that would be a scalar field, and I'd only need the four numbers. I'd need x1, I need x, y, z, and then t. Whereas if we're doing a three-dimensional electric field, I would need x, y, z, the electric field in the x direction, the electric field in the y direction, the electric field in the z direction. So it's like 6 things you need. So that's what a field is. So if you look at the equation for Coulomb's law, which we now switch to F equals K big Q times little q over R squared, you can sort of see that maybe if I divided out the little q, I'd get F equals K big Q over R squared. That's sort of the contribution of the force that you could say is due to the big Q. And that's exactly what we're going to do. We just divided out the other Q. And by doing that, we've created a equation for a quantity whose units are newtons per Coulomb, because before Coulomb's law actually had units of newtons coming out because it was a force. But now we've divided out one of the charges, so it becomes a newton per Coulomb, and that's a unit that we use for electric field. Another one is the volt per meter, and they're actually identical. It's going to take a little while for we get there to see it, but the volt per meter and the newton per Coulomb are both the same unit, and they work fine for the electric field. So that's our idea, is we're going to basically just divide out the little q and say the big Q is responsible for the field. And then if you ever need to actually find out the force on some other charge, it could be little q, or it could be little q1 or little q2 or little q3. All you have to do is take the electric field, which was kq over R squared, for that particular point now, instead of on that particular charge, is at a particular point in space relative to q, the big Q causing the field. If you just take that and multiply it by the charge that you're going to put at that location, say q2, then you will actually get the force. So the electric field is a vector quantity. And of course, if you multiply it by a scalar, you get another vector quantity. And unless the scalar is negative, it's even parallel to the original vector. If it's negative, then it's anti-parallel, it'll be 180 degrees. So that's our idea. The bigger problem, though, is conceptually, when you think about that, if you actually make the argument that one of the charges in Coulomb's law, let's say big Q, remember I had Q1, Q2, and I said, let's change Q1 to big Q, and Q2 is just going to be lowercase q. Well, if you change it to read the big Q as the source, then the electric field equation is going to be KQ over R squared. And if you make that argument, then the argument can also be made that the charge little q also creates an electric field. It just has to. I mean, you can't just argue that some charges create electric fields, but others don't. So what we have to do from a practical standpoint, if we're actually trying to establish an electric field in space or something, we need to imagine taking the Coulomb's law for force, K, Q, capital Q, lowercase q over R squared. We need to imagine dividing that by the lowercase q, but in doing so, we need to also imagine the limiting case as q approaches 0. Because what we need to do is we need to only consider it when the q is so small that it's not necessarily affecting the electric field due to the big Q. So that's where the terminology comes in, but the actual equations are just the same. So let me go ahead and share my screen and get you started on this. Anybody have any questions about what I've said so far? I mean, it's sounded pretty easy, but I did refer to a lot of equations, and I know sometimes students don't follow in their brain quite the way us nerds do. So hopefully this will work out. So what we had was the force, let's say the force on Q, I'll say little q due to big Q. That could be written as K, big Q, little q over R squared, where R is the distance between the center of charge of big Q and the center of charge of little q. And we know the force acts along that line connecting them, and it's either repulsive or attractive. Okay. So what we want to do is imagine coming up with an electric field. And I can actually, even though that equation to the left there isn't a vector equation, I can create a vector out of it if I so desired. But what I'm going to do is I'm going to take the F that I just calculated, and I'm going to divide out the charge that's being affected. Okay. So the second charge is the one that's doing it, and the one that's causing the force. So when I have subscripts like this on a force, the first subscript is the thing feeling the force, and the second subscript is the thing applying the force. Okay. So by me saying F little q big Q, I'm saying the force caused by big Q on little q. So we're going to imagine the electric field as that force, but divided by Q. But like I said, in order to do that, the little q can create an electric field as well. And we want to try to imagine the electric field created without any bastardization from the lowercase q. So in practice, what we do is we'll say that this should actually be the limit as q approaches 0 of F over Q. Now, in this form, I can easily put a vector over it, and you see that it is a vector equation. So when you actually take, and let's say you actually convert this to an equation for F, you can see F is equal to, notice how I ignore the limit. The limit is a thing you do for practical matters when you're physically in a lab and you're trying to do some kind of demonstrations or something like that, or trying to explain it or something. In practice, once you have the electric field, then you're just using this equation, F equals Q times E. So you see that when you multiply a scalar by a vector, which is what you're doing with Q times E, if the Q is positive, then the force will be in the same direction as the electric field. If the Q is negative, then the electric field will be in the opposite direction of F, because F is in the opposite direction of Q. Okay, so this equation is very valuable. And this one is too, except like I said, we never formally actually do the limiting process, okay, unless it's an experimental thing or just to think about it conceptually. Now that you look at that, I think you can see that the magnitude of the force, or excuse me, the magnitude of the electric field is just going to become K Q over R squared. And as I told you, that K is not something that real physicists in general use. So I'm going to write it as big Q over 4 pi epsilon naught R squared. And that's our new equation for the electric field. This would be called Coulomb's law for the electric field. Okay. Whereas this one is Coulomb's law for force. There's actually going to be a third one too. We'll have Coulomb's law. This is a chapter away from here, but I want to warn you. This is Coulomb's law for voltage, and it basically says that the voltage is equal to Q over 4 pi epsilon naught R. Notice the R is not squared in this one. That's a big difference. Notice also that this is actually a scalar quantity. So it has no direction. But the reason why I mentioned this is the blue equations you never, 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 never put in the chart. Well, I say the blue F equation. Let's say this guy and this guy. You never put in the sign of the charge with those two. Okay. This one you have to. So I'm going to say to include the sign of the charge and never include sign of charge. I mean, I say never because I never do it. In principle, you could do it, but I've never found it very useful. So I would say never do it with those two equations. Notice I'm not including it with the F equals Q times E, because putting the negative in there definitely gives you, as a vector equation, gives you a vector pointing in a different direction. So that would be wrong. Okay. All right, now that we've gotten that, and I didn't circle the voltage equation specifically because we're not there yet, so you don't really need to know it. But the key thing to understand here is, remember, Coulomb's law came with a description of how the force is oriented in space. For instance, they told us that it was a repulsive force or an attractive force. It's repulsive if the two charges are both negative, or if the two charges are both positive, then it repels one another. And if the two charges have the opposite sign, one plus and one negative, then it's attractive. And in both cases, the force acts along the line connecting the center of charge of Q to the other center of charge Q. Okay, so that was the case for the force. The electric field, when you do that one, the actual force will act along a line connecting the center of charge of Q, the big Q that's in the formula, to the point P in space where you wish to know the electric field. Okay. So in this case, the R actually goes from the center of charge of big Q to the point in space at which you wish to know the electric field. So write that down some way that you need to, or some way that you can see it, because that's very important. You got to understand that, or you won't be able to compute the vectors that are necessary to solve this. So again, I'll repeat, the force acts parallel to the line between the center of charge of big Q and the center of charge of little q, assuming they're not point charges. They're point charges, it's just from one point charge to the other. And in the electric field equation, they point from the center of charge of big Q to the point P. So then it's along that line that connects P and the center of charge of big Q. It's just a matter of the electric field points in the direction that a positive charge would be compelled to move. So that's the trick as to deciding not only what it's parallel to, which we got from from the point, the center of charge of Q and the point in space, but whether it points one direction along that line or the other is done by imagining a positive test charge at that point P, and then saying what direction would the force on that positive test charge be pointing, and that's the direction of the electric field. Okay. So keeping that in mind, I'm going to try to motivate a more general equation for the electric field. So let's call this our x-axis. Let's call this our y-axis, and let's call this our z-axis. The x-axis is supposed to be pointing straight out of my page. That's how we draw that. When you draw it at a diagonal like that, that normally means it's coming out of the page, and then the negative x-axis would go into the page. The y-axis is perfectly horizontal. The z-axis is perfectly vertical, but both of which are in the page. Okay. Now, we're allowed to put the coordinates and the coordinate origin anywhere we want. We can put the x-axis pointing in any direction we want, and then the y-axis has to be perpendicular to that. And then once you've got those two axes, you just need to make sure that those two axes with the z-axis form a right-hand rule where your index finger, notice I've got my right hand index finger pointing straight ahead with my hand. I've got my thumb pointing perpendicular to that direction, trying to, and then I've got my index finger, or excuse me, my middle finger pointing perpendicular to both. Okay. So the index finger is supposed to be your x-axis direction, the positive x-axis. So in this case, it's pointing out of the board to me, towards me. The y-axis is my middle finger, so that's pointing to that way, which is the same as I have on the board. So my z-axis points up, and I see this one is in fact a right-handed coordinate system, so we're good to go. So always make sure if you have a third axis, you've got to make sure it's consistent with the right-hand rule, or else simple formulas like cross products and stuff like that won't work out. Okay. So now what I'm going to do is I'm going to imagine there's a vector that points to the charge causing the electric field. And in this case, I'm going to say the charge that causes the electric field is an infinitesimal small charge called dq, like differential q. Okay. So I need a vector that points from the origin to that particular charge. So what I'll do is I'll say, let's say this charge right here is dq, and then I will say that the vector from the origin to it is a vector called r dq. Okay. Now, I'm sort of imagining that as if it's in the negative x space. In other words, it's back behind the z and y axis. So it's pointing, not only is it pointing to the left and or to the right a little bit and up a little bit, it's also pointing back behind the page a little bit. It doesn't really matter too much, but I'm trying to picture it in 3D. Now I'm imagining yet another point in space. This point is going to be the point at which we wish to know the electric field. And I'm just going to use the P like you see from Microsoft Word. Okay. So it's a little bit different than a regular P, but it's sort of fancy, but not that hard to draw. So I did that. So I need a vector that locates that spot as well. And that vector points from the origin to that vector, to that point P. And that vector is going to be called R sub P. Okay. Now, remember the actual electric field is supposed to be along the line connecting the differential charge dq, or the big Q in the previous cases. It's supposed to be along the line connecting the center of charge of the Q, the source of the electric field, and the point P at which we wish to know the electric field. So we're looking for some kind of vector that is parallel to that line right there. So I just drew a line from DQ to P. Can anybody tell me a vector operation between RDQ and RP that would possibly give me a vector parallel to that line? You got two vectors, and there's got to be some mathematical operations. So the operations for vectors are that gives the vector as well. So you could add two vectors and that spits out a vector. So that's a category. You could subtract two vectors and that spits out a vector. So that's another category. You couldn't do a dot product because a dot product takes two vectors and spits out a scalar. You could do a cross product because a cross product takes two vectors and spits out a vector, but that vector happens to be perpendicular to both the original two vectors, uh, and its length supposed to be equal to the parallelepiped created by, or the parallelogram, excuse me, created by the two vectors. Something kind of neat there. But either way, you see that would actually be perpendicular to both of these vectors, the RDQ vector and the RP vector. So that's pretty much all the operations we've learned about with vectors. So all we can do is we can add the two, we can subtract the two, or we can cross product the two. Any of those sound like something that might be able to give you a vector that's parallel to that dotted line I just drew? And you can feel free to chat it. I have not got the chat open, but I'm opening it now, just in case anybody said it. Nope, just put names. If anybody hasn't typed their name into the chat, definitely do so now. All right. Well, here's the good news. I've only had like two students answer that question correctly in decades, so it's not anything wrong with you if you didn't come up with it. But the right answer is a subtraction. The addition would work, but remember, when you have two vectors tail to tail, then the vector sum of the two is a vector that goes from the common tail to the diametrically opposed vertex of the parallelogram created by the two vectors. So you would see that that vector would be way across here like that. So that's not what we're looking for addition. Cross product would actually make a vector that would point this way. That is definitely not parallel to the dotted line because it's literally perpendicular to it. So it can't be that one either. So we're just left with subtraction. And more specifically, I need a very specific subtraction. I need the line, because we're going to pretend the dq is positive. And if it's negative, it'll actually be inside of the symbol negative q. And then when you actually multiply it by this vector, for instance, because the number's negative, it's going to change the direction. So it's sort of self-fixing. So if we imagine dq is positive and we want it to find the direction of the electric field, we have to then imagine that there's a charge at P that's also positive. So with that in mind, we would see that we really need a vector that points from P to DQ, like that. Okay, because if DQ was positive and we put a positive charge at Q, then the electric field at P, I said a positive charge at Q, I mean a positive charge at P. Then if I put a charge at P, that charge, if it's positive, would actually be feeling a repulsion. Okay, so let's see. I wrote that backwards, stupid Ed. Oops, hate it. This keeps doing that. So that is the actual direction of this vector, because again, if I put a positive charge at P, you would agree that since dq is positive, then the charge that I put at P would want to move in exactly the direction given by that blue arrow. That blue arrow is going to be RP minus R dq. So that actually gives me exactly the direction that I want for my electric field. So if I took the electric field formula, E equals KQ over R squared, and multiplied it by that vector, it would at least be parallel to the actual electric field. So that's a good thing. But it would be a little jacked up because the formula is all wrong now. So what we're going to say is there's a differential electric field, DE, that is equal to dq, and I'll explain some stuff about that in a little bit, over 4 pi epsilon naught. And notice that the actual distance between the dq and the p is the length of that vector rp minus rdq. So I'm going to go ahead and write down here that I want the magnitude of rp minus r dq. I want that down here. And if we look at this formula right here, we see that that is squared. So instinctively, you would put a 2 there, and that seems pretty good. But I still have a vector on the left-hand side of the equals with no vector on the right-hand side. So we know that this vector on the right-hand side should be parallel to RP minus RDQ. So you immediately think maybe I should just multiply by RP minus RDQ. Now that works, but the formula, which is supposed to be dq over 4 pi epsilon naught times the distance squared, that was good before I put the RP minus RDQ in the numerator. Now the actual magnitude of that vector is the KQ over R squared times the magnitude of R. So it's literally made the R squared in the bottom the equivalent of R to the 1 power. So that's screwed up. So what we have to do to correct for that is we've got to realize that by putting that RP minus RDQ in the top, we've cut the R squared to an R to the first power. To make it right, I'm going to have to put it to the third power. Okay, so that turns out to be the formula that we're shooting for. By doing this, I've now shown you exactly what all the vector parts are. The only thing I haven't given you is some way to come up with dq. What I'm going to tell you is this is really important to be included, and that is dq if it's like one-dimensional. Let's say we had, for instance, a wire or a piece of, let's say, the wick from a wax candle. If we had placed little charges all along that very long straight wick, then that would be something that's sort of a one-dimensional object. And if you, let's say, measured 400 meters of that wick and measured the charge of that wick, and you did the charge divided by 400 meters, you would get a quantity called the linear charge density. And that is represented by lambda. So in this case, dq would be lambda times the length, which, since we're using differentials, we're going to say it's dl. So that's one of the possible ways we can express dq. In that case, if I had uniformly distributed the charges along the candle wick, then the lambda would be a constant. If I didn't, then the lambda wouldn't be a constant, and it could be quite complicated. But it could also be something like some constant times y squared, or some constant times z squared, or some constant times x, or some constant divided by x, or some constant divided by x to the 3.5 power. So that's, there's all sorts of variable functions that the lambda could be, but if it's uniformly distributed, you can assume that lambda is a constant. Now, if we go up a bit, instead of thinking of a one-dimensional object, now we imagine that you take and smear charge on a sheet of plywood. You know, a sheet of plywood's like 4 foot by 8 foot, and you could smear it all over there nice and smoothly. If it's uniformly distributed, then any, let's say, 1 inch by 1 inch area you find, you could cut that out, measure the charge on that 1 inch by 1 inch area, and then divide that charge by 1 square inch, and that would give you the coulombs per square inch. If it was uniformly distributed, every other little block of that piece of plywood that you did that to would give you the exact same number, even if you didn't actually measure it to be 1 inch by 1 inch. If you took a piece that was 12 inches by 12 inches, the number would still work out to the exact same charge density. That one's called a surface charge density, and it's given by the symbol sigma. So this would be sigma times dA, where dA is a differential area element like dx times dy. Now, the other option, again, if this was uniform, of course, the sigma could be constant, but the sigma could also be a function. But we also have one if the object that is charged is a full three-dimensional volume, in which case you'd use the density, the charge density called rho, and that would be multiplied by dV, where that dV is a volume element, one of which could be dx times dy times dz. Okay. Now, the important thing to know about that is lambda, of course, would have units of coulombs per meter. Sigma would have units of coulombs per meter squared. And that's in the SI units. Of course, you could have them per centimeter squared or per micrometer squared. The main thing is the SI units are centimeters per meter squared, just so you'll have an idea of the form. And then rho would have a unit of coulombs per meters cubed. All of that stuff goes together and is important. So rehashing, R sub P is the vector that points from whatever origin you chose to the point P in space that you wish to know the electric field. R dq points from whatever you chose to be your origin to the differential charge element you're examining as a cause of the electric field. And then, of course, RP minus RDQ is just subtraction, so on and so forth. And the DQ has to be either lambda DL, which almost always turns out to be like lambda times DY, or lambda times RD theta, or something like that, and so on and so forth. Now that we have that, I'm going to attempt to solve a fairly straightforward problem that's not unlike the one in your book, only I'm going to do it differently. And you can look at the books one as well. In my opinion, Giancoli has found a really nice, ingenious way of physically coming up with a way to work through this problem. And in my estimation, it's pretty smart physics that he applies to do it, and that's a good thing. But it's my discovery that at least the students I have, they often aren't that physically savvy of making changes like he was doing in that particular problem, but they're sometimes a little better at making sure they just do the everyday stuff of math. So what I'm going to do is make it a little bit more mathematically intuitive as opposed to physically intuitive, and see if that helps you. What I care about, though, is that you can do these types of problems some way. Okay, so if you can't do it my way, and you can do it some other way and can do all of the problems like I'm getting ready to do some other way, then you're fine. But if you can't do all of the problems your way, then you haven't learned that way that well. Okay, so let me start off with computing the electric field, specifically a distance r away from an infinitely long, uniformly charged wire. Okay, so I want to know the electric field a distance r away from a infinitely long wire that has a uniform charge along it. Okay, so I'm going to start off with just the x and y coordinate system, or coordinate axes, because I really don't need any more than x and y. So there's my y-axis, and this will be my x-axis. That's x, that's y. Now, what I'm going to imagine is I'm going to have a really, really long straight wire. That's not supposed to, ah, darn it. Let's do this. Okay, so that just went all the poopy. I know what I'm going to do. I'm going to do that. Okay. And I'm going to do that too. All right. So now I'm again trying to draw a really long straight line. Oh, great. Now it moves both of them. That's just aggravating. Okay. So what I'm going to do is undo that. Now what I'm going to do is just draw a line way over here. And now I'm going to pick this line up and move it to there. Now I'm going to draw another line. I'm going to pick this line up and move it to here. So that's supposed to represent the wire. And in fact, it goes on, whoa. In fact, it goes on infinitely far that way and infinitely far that way. Okay. Now I'm going to go over here some distance away, and I'm going to say this distance is R. Okay. And this point right here is the point P at which I wish to know the electric field. Notice it's a distance R away. We're going on the assumption that we know R, and we're going to have to come up with a formula, a integral to calculate the total electric field. So what I'm going to do is I'm going to remind everybody that our differential electric field vector is dq times rp minus r dq. All that divided by 4 pi epsilon naught absolute value bars, which means the magnitude of rp minus r dq. And again, it looks like a 1 over r cubed law, but it has to be that way just because of the way the magnitudes cancel out. So now I need a vector rp. Can anybody give me what they think the vector rp is? You can use I hats, J hats, K hats, that sort of thing. Would y'all agree? Remember, RP points from the origin of whatever coordinate system you chose to the point P. Does that help anybody figure out what the RP vector would be? Okay, so it has to point from
Would
the
it just
origin.
be P I
What?
hat? Would it just be P I hat?
Not P, but R I hat would be right. Yeah.
Or
Yeah, P is supposed to just be a symbol representing the spot, but R is the distance. So
oh,
yeah,
okay.
you're
Or I hat.
exactly right. The main thing is you got the physics part of it right. So I'm going to draw this vector right here. And this vector is R sub P. Okay. So we're going to say R sub P is just R I hat, just like you said. Okay. Now, when you're doing this kind of thing, it's instructive to make sure if you take a arbitrary point for DQ, it's instructive that you choose that point in the first quadrant, or if you have to put it on an axis, put it on the y-axis or put it on the z-axis or put it on the x-axis. That's just a good rule of thumb to use. I'm going to say that we have a differential charge element right here. And of course, you probably remember the terminology used in your calculus class is from R to R plus dr. Remember hearing that kind of terminology when they're talking about integrals? I always thought it was kind of odd that it was R to R plus dr. I sort of pictured it as R minus dr over 2 and then R plus dr over 2. But no, they were saying it's R plus dr, and the other edge is just plain R. So given that statement, can anybody tell me, knowing that this is along the y-axis and therefore you're welcome to use y as a variable, can anybody tell me what the vector r sub dq would look like? Can anybody tell me the formula for it using I hat, j hat, k hat stuff or anything like that? Okay. What this one has to be is a vector from the origin to the DQ. So I'm going to draw it right here. Notice I'm just using an entirely different color, just so it'll be easy for us to make sense of. And that vector is R dq. And of course, R dq can be written as Y and then J hat.
So because you picked a point on an axis and you formed a right angle, can you just use the law of triangles? A squared plus b squared equals c squared?
Yeah, in fact, I'm going to be using that so much that it's even going to infiltrate my integration process.
Okay.
So, yep, yep. And I haven't labeled the other one, but I will now. I think I've got enough room. This is R sub P, like that. Now, of course, we also have to calculate all the other junk. What I see here, for instance, this is DQ. And I said the charge was uniformly distributed along this wire. So that means it's going to be some constant times the length of it. And the length of it, of course, is dy. So I'm just going to call dq lambda dy. So that's another part we had to work out. I also have to figure out what is rp minus rdq. You can see that's quite easy. It's r I hat minus y j hat. And of course, when you go to add, or in this case, subtract two vectors that are tail to tail, what you do is you take the vector in the subtraction, the one that's negative, that would be, for instance, the dq, the r dq. You turn it around the opposite way, and then you make it addition. So what I would say is I would put this vector arrow right here and then run it this way. And what we'd see is that is negative R dq. Now they're tail to tail or head to tail. So you can actually draw the sum, which is actually a subtraction, as the vector from the tail to the head of the last one. So in fact, what I'm going to do is I'm going to use this sort of pinkish color to represent that vector. So that's the vector RP minus RDQ. Okay. That makes sense to everybody? Now I bet you can easily tell me what the magnitude, because that's another thing we've got to calculate. You can probably easily tell me what is RP minus RDQ's magnitude. I'll give you a hint. Square root.
Square root of r squared plus y squared.
Exactly. Excellent. Good job. So now we've got all the parts of that weird looking equation that I derived for you. So that's what we're going to do now. I'm going to go ahead and build the integral. So what I'm going to do is say E is equal to the integral of dE, which equals, notice I am going to have a lambda because this dq is going to be lambda times dy. That lambda is a constant. The 4 pi epsilon naught, that's a constant. That lambda is a constant. So what I'm going to do is I'm going to write lambda over 4 pi epsilon naught out in front of the integral. And then I'm going to write integral dy, because it was lambda dy is what dq was. And then that's times r I hat minus y j hat. Okay. Now, the good news is when you're using I, j, and k vectors, they can just go through forward and backwards through integrals and derivatives because they're truly constant vectors. Whereas if you're using the unit vectors from spherical coordinates or cylindrical coordinates, those you have to, I usually break them down into I, j's, and k's and then integrate them. But as long as they're in I, j, and k, you can just pull them out in front. Now I've got to take and cube the magnitude. So that's going to be r squared plus y squared to the 1/2 power, but then I cube it, so it's going to be to the 3/2 power. So we're going to get lambda over 4 pi epsilon naught times, in this case, I'm going to get the integral of r dy I hat over r squared plus y squared to the 3/2, and then minus the integral of y dy j hat over r squared plus y squared to the 3/2. I'm sorry about it looking so small in there. The next line will be a lot clearer, but I just wanted to write it all in. There's obviously a curly bracket down there. That's actually what we have to work with now. Okay. So the next line I'm going to say is right here. I'm going to put this lambda over 4 pi epsilon naught out front again. There's my curly bracket. Now what I'm going to do is, since the integral is over y in that first integral, the r can come out in front, and I'm just going to write r I hat. Okay. And then that's going to be the integral. And this time I'll go ahead and put the range of integration on the integral. It's going to be the integral of dy over r squared plus y squared to the 3/2. And this is going to be y approaching negative infinity to y approaching infinity. Okay. Now, physically, let's look at something real quick before I go further. From a physical standpoint, we might be able to make this problem a little easier by excluding certain integrals and stuff. So notice I'm going to draw this in, let's say, dark blue. You can sort of picture that as our dE vector. And you could see maybe this angle is theta, and that would be the same thing as that angle. But the main thing that I wanted you to see about that is we're going to have with that a positive x component, but we're going to have a negative y component. And then if you go further and imagine a diametrically opposed charge on the opposite side of the origin, then what you'd get is at about a little bit more than 3 squares up, you get this, and you'd get, in fact, another dE vector that would go from here to here, and that would make, or another RP minus RDQ vector, that would make a DE vector up here, and that would also have a positive X component, but it would have a positive Y component too. So does that make sense? Do you see that this should have no Y components for this electric field? Because the Y components of two spots cancel each other out. And for every spot you have above the x-axis, there's a mirror spot below the x-axis by the same distance. And those electric fields for those two spots are going to have the same x component. So that's going to double, but they're going to have opposite y components. So they're going to cancel out. So we actually expect the second integral to go to 0. That's from the physics of the problem. So this is the ingenious part that I said your author's doing, the textbook author, Giancoli. He's sort of being physically ingenious by recognizing the symmetry. I'm not taking that step. I'm still going to carry it out, but I wanted to point it out to you so you can see it. Now, if you want to think about it mathematically, which is, I think, something y'all get more, you know that when you integrate an odd function over a symmetric range, then the integral will be 0. The classic odd function is, I'm going to draw it right here and then I'll erase it. But the very classic odd function, does anybody know off the top of your head a classic odd function? This is the even one right here. And then the classic odd function would be this guy. Okay, so this is an even function, and y equals cosine x is an archetypal example, and this is an odd function, y equals sine x. And what you see is, because it's an odd function, basically if I go from negative pi to positive pi, that's a symmetric range, then all this will be negative, and it's exactly the same size as this, so the integral is going to be 0. If I go out to 2 pi and to negative 2 pi, the same thing's going to happen. So the integral over a symmetric range of an odd function is 0. How do you tell whether it's odd? Well, an odd function is such that f, let's say odd, f of negative y is equal to the negative of f of y. And the even function, f of y is equal, or excuse me, f of negative y is equal to f of y. So you can see, for instance, if we use pi for the argument, then we're going to get -1. If I use negative pi, I'm going to get -1 as well. So cosine is an even function and sine is an odd function. If we look at this integral right here, do you see if I replace in this part, if I replace y with negative y, this gets me a negative. This one gets me a negative, but it's squared, so nothing happens to it. But what you see is, because of this y up here, when I switch from y to negative y, I actually get the negative of the integrand that I had before. So this function is clearly an odd function. And since the range of integration is from y equals negative infinity to y equals positive infinity, that too is going to be 0. So now I showed you a mathematical reason why it should be 0. I'm going to go ahead and erase all that stuff. Of course, you can see them on the video anytime you want, but I need the space. And I'm also going to erase this. Okay. So we do expect that to go to 0. Now I'm going to do the other integral, and the other integral is first a negative. I can't pull the y out because that's what we're integrating with respect to, but I can pull the j hat out. So I'll put the j hat out in front, and I'll take the integral from y approaching negative infinity to y approaching infinity. Remember, you take the limits. That's how you do those improper uh, integrations. This is going to become y dy over r squared plus y squared to the 3/2, like that. Okay, so that's the problem in a nutshell. For this one, though, for the first integral, I'm going to say let y equal r tangent theta, then dy is equal to r secant squared theta d theta. For this integral, I'm going to say let u equal r squared plus y squared, which causes du to be 2y dy. So that's what I'm going to do with these two integrals. I'm going to say lambda over 4 pi epsilon naught, curly bracket. I'll probably have to break the second integral on the next line, but that's okay. I'm now going to put the r and the I hat out in front. So there's an r and there's an I hat. I'll leave the range of integration off for right now. The dy is going to become r secant squared theta d theta. And in the bottom, this is the cool part, we're going to get r squared plus r squared tangent squared theta, and all of this will be to the 3/2. Now I'll also say minus, now I'm going to do the other integral. The other integral is going to have a j hat in front of it. I'm going to also multiply it by -1/2 so I can multiply by 2. So I'll put a negative in front of that and just put a 2 on there. So now I've made that first negative sign into a fraction bar. And by doing that, multiplying by -1, or excuse me, multiplying by 1/2, I can put a 2 right here to cancel that out so that this would become 2y dy, which is what du is. So now I can go ahead and write the integral of du, and actually I'm going to leave a space. I'm going to say the integral of du, and notice I made r squared plus y squared u, so that's just basically going to be u to the -3/2. So that's what our new integrals are. Notice I can factor out from this part right here, I can factor out the r squared because it's a common term in both of them. So I'm going to do that. And notice when I factor it out, it'll become r squared times parenthesis 1 plus tangent squared. But not only that, the r squared is being raised to the 3/2 power. A power raised to a power means you multiply the exponents. So 3/2 times 2 gives you 3. So that means it's going to be r cubed in the bottom. And this r and this r is going to make r squared on top. So now I get lambda over 4 pi epsilon naught, curly bracket, r squared I hat over r cubed, times the integral of secant squared theta d theta over 1 plus tangent squared theta to the 3/2. Can anybody recall from your trig identities what 1 plus tangent squared is? it's secant squared theta. 1 plus tangent squared equals secant squared. There's another one, 1 plus cotangent squared equals cosecant squared as well. But anyways, that's one of the identities that we're using. Now, notice that's a secant squared under the 3/2. So again, you've got something squared and then raised to the 3/2 power. So you multiply 2 times 3/2, you get 3. So this is ultimately going to be a secant squared over secant cubed, which means the secant cubed is going to win. So it'll just be secant in the bottom, but 1 over secant theta is the same thing as cosine theta. So this whole integral is just going to become cosine theta d theta. The other integral, on the other hand, that's going to be negative 1/2 j hat. Now, the integral of u to the negative 3/2 is u to the negative 1/2 divided by negative 1/2. So what I'm going to do is multiply it by -2, because dividing by negative 1/2 is the same thing as multiplying by -2. So I'm going to put that over here and say times -2, and then it'll be 1 over r squared plus y squared square root. Okay. And this is supposed to go from y approaching negative infinity to y approaching infinity. Okay. Now I'm going to go to the next line and say lambda over 4 pi epsilon naught. This r squared over r cubed is just going to become I hat over r. And like I said, the secant squared over secant cubed is going to become 1 over secant, and 1 over secant is cosine. So I'm now going to get the integral of cosine theta d theta. But here's the neat thing. When I made that trig substitution, I created a scenario where we can look at a triangle like this. Now, this is a nice trick when you're doing trig substitution, and it works a lot in physics. What I said was tangent theta essentially is the same thing as y over r, because I said y equals r tangent theta. So if this is theta, then tangent theta is supposed to be opposite over adjacent, and tangent theta is supposed to be y over r. So I'm going to put the y here and the r here, and then that means this is the square root of r squared plus y squared. So realizing that, I can see that when y goes to positive infinity, what's theta going to become? Notice theta is the same theta as I drew in the diagram up at the top left. What would theta become as the tip of that wire went all the way to positive infinity? What angle above the ground do you have to look to see it? Would y'all agree that that's 90 degrees? So it will be 90 degrees. Just imagine if you went up and looked at an apartment building that's 4 stories, you'd see your head craning up like this to see it at the base. If it was 10 stories, you'd have to open up a little further. If it was 20 stories, further still. If it went infinitely far, you'd have to look straight up. Okay. So in principle, I could have used the evenness of this integrand. Notice this integrand, if you replace the y with negative y, it only appears there. So this is actually an even one. So one of the things you can do with the even function over a symmetric range is I could change this to 0 and then multiply by 2. That's one way of doing it. I chose not to do it, but I just wanted to let you know that's a time saver. So what I'm going to do is I'm going to say from negative pi over 2 to pi over 2 is what we're integrating to. And of course, pi over 2 means 90 degrees. Now the other one, we're going to have to do this with. So I'm going to say -2 times -1/2 is ultimately going to give me positive j hat. The 2's and the 1/2's canceled out. And what I have to do is, I'll use a square bracket. What I have to do is take the limit as y approaches infinity of 1 over the square root r squared plus y squared, and then subtract from that the limit as y approaches negative infinity of 1 over the square root of r squared plus y squared. Okay. I think you can see that clearly that's going to be the same answer for both cases. So the two subtract to give you zero. In other words, let's look at it. When I take the limit as y approaches infinity, the r becomes irrelevant and it just becomes basically 1 over y. And then I take the limit as y approaches infinity of 1 over y, I get zero. And the same thing over here, it's the limit y approaches infinity of 1 over y, which equals 0. This one's going to be the same thing. The limit of 1 over y as y approaches negative infinity. Again, that's just going to give you 0. So 0 minus 0 gives you the whole thing is 0. So mathematically, we went ahead and showed that that integral would be 0 anyways. Now I can do the other integral. Since I don't have those other terms, I can go ahead and put the I hat and the R with the fraction, well, with the constants out in front. So I'm going to say lambda over 4 pi epsilon naught R times I hat is the constant, and then all I have left is the integral of cosine theta. We know the derivative of sine is cosine, so the integral of cosine is sine. So I'm going to get the sine of theta, and that's going to be from negative pi over 2 to pi over 2. So this is going to be lambda over 4 pi epsilon naught r I hat times, now the sine of pi over 2 is 1, and then the sine of negative pi over 2 is negative 1. So I end up multiplying by 2, basically. This whole quantity right here is just 2. So ultimately, the answer becomes lambda over 2 pi epsilon naught r, pointing in the I hat direction, and that is the electric field. As I was telling Carter earlier, this is literally the most difficult, the second most difficult problem of the whole semester. And the other one is just moderately harder. In fact, it even reduces down to the same integrals. I even used the same trig function substitution and the same u substitution with that one. The difference being, though, in addition to having those vectors inside the integrand, you're also going to have a cross product of a vector. So it really is kind of big, but I'll show you how to do it. So don't feel bad if this feels like you just got blown away. Okay. That's perfectly normal. But I do recommend you go back and watch this and even read the equivalent example that your book does. And probably between seeing this twice by me and once by the book, you probably can figure out some happy ground where you sort of understand both solutions. What I will tell you is I sometimes will make up an equivalent of this to give on a test or a midterm or a final. And the only difference might be instead of it going from negative infinity to positive infinity, I could say let it go from, L or negative L to positive L. Or worse, I could do something like let it go from negative 10L to positive 2L. So it's not symmetric. I could also change up the lambda. Instead of it being uniformly distributed, I could say that the charge density, the linear charge density, is a function of y, and I'd call it some, constant c times y squared, and then you could do the integral that way. Okay. Now that would be an entirely different integral because instead of just lambda times dy, you'd have c times y squared dy, and the whole integral process would be a little different, but you could still work it out. So I definitely try uh, computing this when it's not going from negative infinity to positive infinity, but rather from negative L to positive L, and then try it from negative, 10L to positive 2L, or from negative 2L to positive 5L, or some different stuff like that. If you do it a couple times, you should be able to make enough sense of it where you can learn how to do it. Okay. Anybody have any questions on this one? Okay. Well, if you look in your module for I think for this week I already put it up, but there's videos where I've done this problem as well as the next three that I was going to do. I've done them before in the past in classes, and I think one of them's called three ingenious integration problems or three tricky integration problems or something like that. You can look up there because I really wanted to spend time to do a second one, but I don't have enough time now. So I'm just going to go ahead and let you guys go. But definitely do this and pay attention if I post any videos. I did tell you all I'm moving your test. Instead of it being due this week, you'll have until Sunday of next week to get it done. Check out, make sure you find out what you need to do at the testing center, whichever testing center you're going to, find out their hours, make an appointment, see if you need to bring an ID, all that kind of stuff. And that's it. You guys have a good evening and thank you for coming. And I'll wait for the last person to leave in case anybody has any questions. If you didn't already chat me your name, make sure you do, please. Micah or Giovanna, y'all have questions or maybe not here anymore?
No, I'm here. Sorry.
Okay, no problem.
Have a good one.
You have a good one too, Giovanna. How about you, Micah? You there, bud? It looks like a no. So I'm going to go ahead and say bye, everyone. Thank you for coming and bye-bye.